Hello, professors and students. My name is Jeho Hwang from Korea Maritime and Ocean University. Thank you for your interest in my research topic. In this presentation, I will address the topic about ballast water management system for bulk transport vessels, sustainable energy use. The presentation table is as follows. The level of industry responsibility for global air pollution is high. Moreover, it has adverse effect in a wide range of scopes, such as accelerating global climate change, causing human disease, and destroying ecosystems. When continuously exposed to area with severe air pollution, people could experience primarily sensory abnormalities in terms of vision and breathing, which can cause continuous health problems. As a result, the UNFCCC was adopted in 1992 in response to the acceleration of global warming. And in the future, the Paris Agreement was adopted in 2015, following the Tokyo Protocol and the Marrakech Agreement. To solve the global air pollution problem, IMO, which operates environmental sustainability for the maritime industry, is also promoting various technology development support and policy development and implementation in the range of technological, operational, institutional, and market-based sectors. Also, global regulations for preventing air pollution caused by merchant flags have been strengthened by IMO over time. IMO adopted strategy to prevent greenhouse gas emission caused by vessel operation by more than 40% until 2030 and by 70% until 2050 compared with 2018. Ultimately, policy and technological efforts are being made in parallel under the slogan of net zero emission by 2050. This is an early stage in which plans to reduce emissions in the area of logistics, energy efficiency, speed reduction, fuel and pathways are being implemented to support net zero emissions. The emission reduction rate was found to be high in terms of energy efficiency next to fuel area according to IMO strategy. For example, EEDI, EEXI, CII, and IMO TCS are mandatory. On the other hand, EEOI and SIMP are recommended by IMO. In the long term, the improvement in vessel energy efficiency is in the maritime industry has become an essential part of long-term operation and development, as shown on the slide. To respond to the increasing regulations on vessel fuel and energy efficiency, various studies have been conducted on propulsion system and eco-friendly energy sources. As a result of reviewing previous studies, The scope of previous research related to PWMS is limited to methods aimed to improving ballast water stabilization efficiency. In addition, research topics on eco-friendly ships were mainly studied on eco-fuels. However, in this study, PWMS operation has been envisioned as a new green technology that is energy efficient, and it has the potential for self-power generating in power in pipe structure. The PWMS is an essential module that is crucial for maintaining vessel stability while reducing the stress on the hull during voyages and cargo handling processes, and improving overall navigation efficiencies such as operability, propulsion, and maneuverability. This study adopted the Savonius turbine system, adopting a deflector for minimizing the variation in the function of in-pipe parameter in the PWMS. Figure 3 illustrates the PWMS-based power generation method. The efficiency of using the hydraulic energy of a flowing liquid can be realized by incorporating a deflector into the Savonius turbine to improve the performance of the electricity restricting device module in the pipeline. Overall, a significant amount of power can be generated while maintaining stable PWMS operation, not disturbing flow characteristics. Under PWMS operating conditions, the surplus pressure energy produced by seawater flow via a deflector is considered to be a result of potential energy restriction. In this study, a bulk carrier was introduced for the PWMS-based self-power generating system. The reason is that the ballasting and deballasting procedures were performed continuously during cargo operation according to the PWMS plan, based on the statutes of the asymmetric cargo and ballast distributions in each compartment. The bulk carrier selected for this case study is the CX0811, and its overall characteristics are as follows. From the structural point of view, CV0811 has 7 cargo holds and 12 ballast tanks. This slide depicts the detailed location of each cargo hold and the ballast water tank. The proportion of ballast water capacity accounts for 18.68% of the maximum volume the vessel can accommodate. When the PWMS is activated, the flow velocity in the interlocking pipe structure is continuously measured using each flow measurement unit, FMU. In the pipeline near the FMU, the fluid flows in the same direction and passes through during ballasting and deballasting operations. The drive source devices can be installed in 2 pipe sections with respective lengths of 2,170 mm and 1,830 mm. The location where ballast water flows in the same direction during system operation are denoted by blue lines, which in front of each FMU. The data collection period for the study was from July 19, 2020 to March 4, 2022, and Ballast was performed 18 times and Ballasting performed 23 times, respectively. The time series data of FMUs, which is a part of ECS log data stored in the database, was collected. The flow rate measured from FMU during BWMS operation is a total of 31,651 data, and it is classified into 7,387 for FMU1 and 5,857 for FMU2 in the ballasting process, and 10,354 for FMU1, 8,053 for FMU2 in the deballasting process. The volumetric flow rate characteristics is represented in Table 5. The power output that could be obtained from the hydroelectric system can be circulated basically using equation 1, and the turbine head in equation 1 corresponds to the surplus of pressure difference in a power network corresponding to equation 2. In equation 3 and equation 4, numeric value may appear if the individual sizes are specified in different units of measurement than previously specified. The unit of M is converted to ton per hour. The power source obtained on the pressure difference between point PIN and PTE is expressed in equation 5. In the system, the power output from the operation of the combined module of Savonius hydro turbine and deflector designed to generate from the pressure difference between point PIN and PTE can be expressed as equation 6. According to the pipe specifications, which is a turbine aspect ratio of 0.9, which is the ratio between the vertical and horizontal length of the turbine, a blockage coefficient of 0.8, which determines the deflector geometry, and a deflector angle of 50 degrees and 80 degrees, for which the required pipe length is 186 mm and 239 mm. The efficiency range of the generator is approximately 85 to 98%, and the efficiency of the electric power converter is 97 to 99%, and the efficiency of Savonius turbine with deflector is 12% at 50 degrees and 16% at 80 degrees, where the engineering parameters were assumed to be the same level, which is applicable to the geometrical condition. In summary, the total power produced during data collection period in the blasting was 2,152 to 41,140 kilowatt at 50 degree and 3,280 kilowatt to 41,140 kilowatt at 80 degree. In contrast, for the ballasting, the power production range was circulated as 1,459 to 31,451 kilowatt. And kilowatt and 2,219 kilowatt to 47,135 kilowatt at 80 degree. The circulation result of the amount of power charge per hour are presented in figure 9. The range in which electricity could be generated per hour is 863 to 2,503 kilowatt per hour at 50 degree and 1,430 to 4,090 kilowatt per hour at 80 degree. On the other hand, the generation rate during deballasting is 1,256 to 3,024 kilowatt per hour at 50 degree and 1,970 kilowatt hour to 4,744 kilowatt per hour at 80 degree. This study affirms that the possibility of improving vessels' operational efficiency by utilizing BWMS, which could be developing the eco-friendly shipping industry, combined with various power generation industries. In addition, bulk carrier accounted for the second largest share of 22.39%, about 12,258 vessels in 2021. Therefore, this system could have a large impact in achieving the aim of developing eco-friendly vessels more efficiently to enhance energy efficiency and create benefit in the bulk sector of maritime transportation and related industries. As a limitation, this study cased only the bulk ship CX-0811 and power production capable of potentially developed was circulated compared to simulation, which could drive more accurate results. In the future study, based on the actual design of the module for more accurate demonstration, more sophisticated analysis would be achieved by a substantially reduced simulator. Thank you for listening.